right, so it's a pleasure to have Matthew McCullough here from CERN, who's opening the day with a talk on cosmological approaches to the electroweak hierarchy problem. Thank you very much for accepting the invitation.
Okay, thanks, Raffaele. I took this photo yesterday, and it made me think a little bit about where we are. And in the context of this talk, I think this is quite an auspicious hill on which to give the talk. This is just next door is where Fermi sort of started to figure out the statistics of the quantum statistics of fermions, which is really at the heart of matter at that time. But also this is where Galileo spent a lot of time pondering the cosmos. And so it's sort of auspicious in a sense because these cosmological approaches to electroweak fine-tuning essentially try to draw together these two themes to see whether cosmology and dynamics in the universe, the early universe, can address questions we have about microscopic physics, and our current best understanding of microscopic physics is at the electroweak scale and no smaller. It's also auspicious, however, because this is also a place where Galileo spent the last years of his life under house arrest for his heretical views, and this is something I can't fail to keep in mind when preparing. I didn't fail to keep in mind when preparing this talk, because of course some of these views, some of these arguments or speculations could be viewed as heretical, depending on your perspective. So a very auspicious place to give this talk, and I'm very pleased to be able to do it. So what's the backdrop? I need to sort of frame the question we want to answer before I start discussing the various theories. So for every scalar that we have encountered until the Higgs, it had properties that were calculable within some more fundamental microscopic theory, you know, properties of the scalar fluctuations and the scalar the Landau-Ginzburg field and Landau-Ginzburg theory for superconductors was ultimately superseded by BCS theory, which is the more microscopic understanding of this field, and the condensate as being a condensate of electron pairs. For pions, for instance, the chiral Lagrangian is a great phenomenological Lagrangian. It has many beautiful aspects, but it was ultimately superseded by some microscopic theory, which was QCD, gluons, in which we can then calculate the properties of pions. And this is not just related to scalar fields or these scalar fields, but many revolutions in physics have been essentially a revolution in going to the next layer of reality and our next better microscopic understanding. What is the standard model? Well, unless you can answer this question for me, I think it's fair to make the assumption that the standard model will be, not the assumption, I mean, it's the physics is telling us that the standard model will ultimately be UV completed by some more microscopic theory. The standard model breaks down. And then we want to know what that microscopic theory looks like and whether or not we can calculate the properties of the Higgs within that microscopic theory. There is one, I think, still logical possibility, although it's a pretty unpalatable one, which is perhaps there is some microscopic theory in which the properties of the Higgs are just never going to be calculable. The mass of the Higgs is something that you just have to measure by experiment once, and that's the end of the story. You can never, it doesn't make sense to ask the question, where does it come from? I would, if I believed this were true, I would not be a physicist. So then we want to know, so the other logical possibility is that there is a microscopic UV completion because the standard model breaks down, and that within that UV completion, at smaller distance scales, we will be able to calculate the properties of, for instance, the Higgs boson, its mass, its VEV, its coupling, and also, ideally, other properties of the standard model. So right now, we're at this stage where we need to make some guesses about what that UV completion looks like, and we have little pieces of little breadcrumbs that we can follow. Ultimately, ideally, we would want to identify precisely what this UV completion is through a combination of experiment. It cannot be replaced. No amount of theoretical speculation will replace experiment. So we would ideally do experiments at higher and higher energies to greater and greater precisions to identify what UV completion is, and then ultimately construct what the fundamental theory looks like. At present, we don't have high enough energies, and on the theory side, we have an increasingly murky picture. It felt clearer in the past, but I think that was a smokescreen. In fact, it was always murky. But we do have some clues. So the experiment has told us that wherever this UV completion is, it appears to be at energy scales reasonably far above the Higgs mass. It's not at the electroweak scale. LHC said no to that. On the other hand, we can use this information and make some guesses on the theoretical side based on fundamental principles, based on effective field theory arguments. And one of these guesses is known as the hierarchy problem. Essentially, there's no, at the electroweak scale, there's no symmetry that can comfortably accommodate a scale separation between the UV completion and the electroweak scale. And so this leads to a puzzle, which is known as the hierarchy problem, which is how such a scale separation could have come about. Now, there are many ways of addressing this. Perhaps this scale separation is just an accident, sort of an accidental fine-tuning at the few % level or something like this. Perhaps we've deeply misunderstood something about quantum field theory. Or perhaps the sort of symmetry-based program to answer these questions wasn't so far off the right track. Maybe minimal. It's not minimal SUSY. It's not some minimal composite Higgs model, but the usual EFT-like arguments on symmetries and selection rules are correct, but we just actually haven't managed to identify the right theory. I'm certainly of the view that that could be the case. Or it could be that there's a fundamental ingredient that we've just totally overlooked for a long time, and that the way we could hope to answer these questions is actually couched within principles that go well beyond just quantum field theory in Minkowski space. And one of these sort of ansatzes is, I don't know how to pronounce the plural of ansatz, is that perhaps the fundamental parameters of the standard model were somehow evolving in the early universe. They were evolving, and this would require that some scalar field is changing value. And there are a number of theories that have been proposed, but they all have, at least all but one of them, I believe, that I'm aware of at least, have basically some fundamental ingredient that involves some light scalar field. If there's one light scalar field on its own, if we're not going to reintroduce this hierarchy problem that we were trying to understand in the first place, then I think the only good candidate sort of structure in an effective field theory sense is for this scalar to be a pseudo-Nambi-Goldstone boson. That can be the only way to have a single a solitary light scalar for presumably a spontaneously broken approximate U1 symmetry. So it has an effective field theory selection rule. There's some decay constant, I'm calling it little f in this talk. It can have all sorts of terms in its potential, all sorts of derivative interactions. But if we want to consider the question of electroweak naturalness, it would couple to the Higgs. And so as phi changes value, the effective mass squared of the Higgs can change value. You can do a shift symmetry, a shift on the field that's unphysical. We're not making any fine tunings in the theory or something like this. This is just a standard shift of a field, a reparameterization, which essentially sets, for my purposes in this talk, sets the origin of the scalar field to be at the point where the total Higgs mass squared is 0. And that includes all quantum corrections and so on. This is not a fine tuning, it's just an unphysical shift. It's just a choice of basis. And then there's some potential that has a selection rule that looks like this. There's some coupling, some decay constant, and we're careful to get all of our units right. And presumably all of these C's would be order 1-ish parameters. We don't know exactly, but there's no reason, unless there's some selection rules, for any of them to be hierarchically small. Okay, and so perhaps there's some scalar field. It has a potential, it couples to the Higgs, and we explain why the Higgs mass is small compared to the microscopic scale in the theory, which is some cutoff that I will call big lambda. However, we can see that this theory alone does nothing special. The point where the Higgs mass squared is small is completely uninteresting as regards this scalar field phi. So at the point where we can integrate out the Higgs, depending on whether its mass squared is positive or negative. When its mass squared is positive, integrating it out essentially sets it to 0. So the scalar potential looks like this. When it's negative, the Higgs gets a VEV. You can integrate out its effect to find the effective potential for phi, minimizing in the Higgs as you go along. And it looks like this. Consistent with effective field theory, this lambda can't be too big in terms of these parameters here. Otherwise, there'd be some hidden hierarchy, some fine tuning in making these small, but having a big coupling in here. And so it looks like this. Now we can see if you differentiate this scalar potential with respect to phi, the point where there's an extremum where v prime is 0 is not anywhere special. It has no relation, no special connection to the point where the Higgs mass squared is 0. So in general, the critical point is not generally an extremum of the scalar potential, unless you start to fine tune things. Say you set this term to 0 and set this term to 0 or something, then of course v prime will be 0 at the point where phi is 0. But that's just a fine tuning that you're putting into the theory that you were trying to avoid in the first place. So you could say, well, this is maybe, this term here is a loop factor smaller than they would naively expect. And then so you can get a loop factor close to the critical point, but you may as well have just argued for the same loop factor in the Higgs mass in the first place. So I don't see that one really gains much in that direction. Yep. Yes.
Was to absorb the PO8 squared term?
Yes.
Okay. Thanks.
Yeah. Yeah, exactly. So that term includes all of the pieces. Yep. So what are the ingredients we need? The ingredients we need are, there are two that I can identify that are sort of common themes for all of the models. Of course, I went through the models first and tried to figure out what these themes were. The first is you need some reason why the critical point is special for this evolving scalar field. And the second is that you need some way to get to the critical point. The scalar field, there's no reason for its initial condition to be peaked at the critical point. And so somehow you have to find a way for the scalar field to want to be there and for it to want to stay there after a long period of cosmological evolution until the present day. So now I'll go quickly through a number of models which satisfy both these criteria, but in slightly different ways in each case. The first is the prototypical example, which is the relaxion, where phi is also coupled to GG joule. The super important thing here is that this term here is a total derivative. So underneath the bonnet, this is a derivative coupling. And so perturbatively, regardless of the scale of big F, this isn't little f, this will never generate any perturbative corrections to the scalar potential. It does give you non-perturbative corrections, of course, which look like this. They depend on the Higgs VEV, and they are calculable. And so the really, in my view, the really smart thing here is that big F can be much smaller than little f. So the decay, the periodicity of this potential can be much shorter than the general overall field range for this scalar field. And what this means is that this makes then the critical point special, because once you get to the critical point, these additional wiggles turn on and they have a small periodicity, and which means that their gradient can, even if their overall coefficient is small in terms of the cutoff, their gradient can overcome the gradient of this potential, which has a large periodicity. So that's the trick. I still, to this day, I still think it's really clever. And so the way to get there is that you start with some initial condition that the scalar field is just somewhere up this potential. It will roll down according to slow roll. And because of Hubble friction, it will roll down slowly and settle into one of these minima at a place that you can pretty much calculate. And because whatever this coupling is, G epsilon, can be very small, and regardless of the size of little f here, you can make it smaller and smaller such that these terms balance when the Higgs VEV is hierarchically below the scales you'd expect in terms of the cutoff. So I'm going to put some footnotes in amongst these slides, just with some things to keep in mind. I don't see them as lethal issues or criticisms or anything like that. It's just something to keep in mind. And one of them here is this doesn't work for QCD. You have to have some new gauge group, and that also implies then you need to have some new electroweak states, which is an interesting aspect. Another class of models involves particle production. This was proposed by these authors shortly after. I'm putting these papers in chronological order, by the way. So there's I'm injecting no personal aesthetic assessment in here. It's just these are important papers in this area, ordered by the time that they arrived. And so here, this scalar field again is coupled to topological terms, but this time it's for the electroweak ones, and it's just electroweak, not QED. One can find symmetry reasons to motivate that. And again, the decay constant can be much, much smaller. So this can be a strong thing compared to the sort of naive effective field theory scale for field range for phi. And additionally, there's some little wiggles. And in this model, you start in the broken electroweak phase. So up here, the effective Higgs mass squared is large and negative. And the field is rolling fast. So it rolls fast and easily gets over these wiggles. But then once it hits the critical point, the electroweak gauge bosons become light. And so the rolling of this scalar field can actually start to produce them. And that leads to an effective friction, which slows it down and means that it can get stuck in one of these wiggles here. So this is a different class of models. There's many interesting aspects about this class of models, but there have been some recent updates regarding the Schwinger pair production effects here, which modify the story a bit. So please look at this paper if you're interested. Inflating to the weak scale was another interesting class of models. Here, these authors have, so this A field is not phi. A is not the thing that's scanning the Higgs mass squared. It's coupled to the QCD topological term, and also there's presumably some other gauge group that's strongly coupled, and then there's two different decay constants. Neither of them is little f. And what happens is that if the Higgs vev is large, the QCD axion-like potential is large, and so that creates wiggles here that the field can be trapped in. So if you start with a large electroweak scale, so large negative mass squared, and then it's the background scalar field is evolving. If it crosses the point where the Higgs vev starts to become small, these wiggles become too small, and this field can roll the whole way down here, and the change in vacuum energy is this lambda h, which can be a big parameter. So essentially integrating out these dynamics, you get an effective potential for phi, or for the effective Higgs mass squared, which looks like this. Beyond the critical point, it drops because A is no longer trapped up here and it rolls down here. So that's the way to make the critical point special, and the way to get there is to evolve up the scalar potential phi through diffusion during inflation evolves up here. I would argue that I think now we would understand that this seems to require eternal inflation, at least in the most vanilla implementation. But one should discuss this with the authors. And Michael's tuned in here, I see, so we can take this up maybe in the discussion session. Footnote doesn't naively work in the simplest implementation because of similar issues to the relaxion for strong CP. And also I think, yeah, it seems to imply to me at least that eternal inflation is required at least for the most vanilla implementation. Crunching dilaton. Here one has the Higgs, which is mixed with a dilaton of some CFT sector. And what this mixing does is that this dilaton has a potential that looks like this. So there's some explicit scale breaking, and there's a deep minimum out here. But near the origin, the mixing allows for a little minimum to be created if the Higgs vev is small. So these patches with a small Higgs vev can live here, but otherwise it rolls down. And what that means is that only if there's some sort of background sort of multiverse or scanning of the Higgs mass squared, then only patches with a small vev will survive, because all of these ones will roll down here and will crunch and give you negative CC. I think here one interesting thing to keep in mind is that there's really a non-trivial interplay with sort of the landscape and cosmological constant values within that landscape and the scanning mechanism, which we might want to discuss. Sliding naturalness from Raffaelli and Daniele also has a landscape of Higgs mass squareds, but there's also a pair of scalar fields with a potential that looks like this, and they're coupled to the QCD topological term like this. And only when the Higgs, because of the back reaction from this topological term, which gives you an axion-like potential, only when the Higgs vev is small and the strong CP angle is small, which in this model, it's assumed that they're sort of scanning, so they have a variety of values in the multiverse. Only if those two conditions are satisfied can both scalar fields have a local minimum near the origin. Otherwise, you see there's a negative quartic here. Otherwise, they would roll out to large field values with large negative CC and crunch. And again, here, I think there's an interesting sort of dialogue between this sort of landscape. I also wonder, Daniela, can maybe answer this for me, if eternal inflation might be required for realizing the landscape of Higgs, where are you, Daniela? Of Higgs mass squareds. It wasn't clear to me from reading the paper, but
it's the same landscape that you use.
Yes.
The simple versions would be with eternal inflation.
Yeah.
And maybe also Daniele wants to comment, but in principle, you need much fewer e-folds than those that you end up with for eternal to just populate all the vacua.
Right.
Then you need a mechanism to exit inflation, but in some sense, in the sorry.
Okay, thanks. So maybe not eternal inflation then, but maybe if the question of populating the landscape, I think, is the guess.
Someone exactly. I don't know if someone has written an explicit model of the landscape without eternal.
Yes. Okay.
You just need to do it. I think Danielle and Michael are doing it actually.
Let's come back to it maybe afterwards, because this is one of the main questions. And I guess I'll just do a couple more minutes. This recent work with Jan and Tavong, which we call self-organized localization. Here, the special reason for the critical point to be the reason for the critical point to be special is quite simple. It uses Higgs metastability. So one can, in the standard model, the plot of the Higgs effective potential, including running, looks like this. As we all know, it's metastable. We're at the origin. But you can just take that plot, and if you have a large negative mass squared, which is larger than the instability scale where the potential turns over, then the effective potential looks like this. So if you plotted the effective potential for that scalar field phi, here it's var phi. If the Higgs can sit in this local potential, so if you've got large positive mass squared for the Higgs and then you reduce it, then it can sit in this effective potential. The scalar potential looks like this, but at some point when the Higgs mass squared becomes too negative, this IR phase doesn't exist anymore. The standard model vacuum has vanished. And so the phase diagram terminates there, just like the phase diagram terminates of for ferromagnet of the background magnetic field. And if the Higgs were to roll all the way down, then there's the UV vacuum, which just has lower vacuum energy density. So the scalar potential looks like this. It's sort of interesting. I hadn't realized before that if you just scan the Higgs mass squared, this is what the scalar potential for that field looks like. And the way for us to get to the top, which is the special point here, the critical point, is to use eternal inflation, these volume effects, which can lead to a volume weighted probability distribution that is peaked at the top of the potential, which is the critical point. Here we had to add something that we referred to in our emails as junk, but of course we didn't do that in the paper, which was that if you need that the instability scale is like 10 to the 11 GeV. So this would predict that the electroweak scale is 10 to the 11 GeV, which is wrong. It's naturally below the cutoff because it's generated by RG evolution. So it can be naturally exponentially separated from the cutoff, but 10 to the 11 is no good. So we had to add new fermions coupled to the Higgs because they drive the quartic negative more rapidly. It becomes negative earlier. And so to get the electroweak scale to be down near the TeV scale, we have to have TeV scale fermions coupled to the Higgs. Okay, and the last one is an outlier. The last one I will discuss. There are other papers, of course, and that's Naturalness, which doesn't have any of these ingredients, but I didn't want to overlook it because I think it's conceptually important. And in this model, there aren't multiple vacua, but there are multiple sectors where there's a distribution of effective Higgs mass squareds, and if you've got enough sectors, then some of them will just be accidentally light. And then, so if you have all of these sectors, and then you can have a naturally low reheat temperature, which will only populate sectors below that reheat temperature, and there's no sort of hierarchy problem for the reheat temperature. And so what this means is that you can have a coincidence, which is the reheat temperature will only populate, for example, the lowest one, but that is technically unnatural. You don't have to fine tune parameters against each other to get that. So it's like the mu b mu problem in SUSY. And this is another way of approaching the electroweak hierarchy problem using cosmology. So what's my personal view? It oscillates, but I personally don't want to give up on symmetry-based approaches. I think there's a lot more to do there, and I'm still very excited about a lot of things in that direction. On the other hand, I don't think we should we should place our standards should be high in terms of ambition and playing by the rules of the game, but I don't think we should avoid being heretics. And indeed, you know, if we look at the past, Galileo or quantum mechanics, for instance, there are many times when progress happened by venturing into a partially not understood framework. And so perhaps one of these examples or some variant of them or something along these lines will turn out to be right, but we may not even realize it, first of all, because it might seem unpalatable in the first place. There's some open questions maybe to leave for the discussion session, perhaps. One is, you know, if a model is in the swampland, for instance, if you have a super Planckian decay constant, that seems to imply it's not in the string landscape. What does this mean? What does this mean for our picture of UV physics? Is climbing calculable? Going up a potential seems to me, at least, to imply eternal inflation. Does that, then you have the measure problem and all sorts of issues like that. So are we even calculating and observable? Is there any hint of a unifying principle? I can't see one necessarily. Are electroweak scale states always going to be necessary in these sorts of models? They do seem to pop up. What would this even imply for us? I sort of really hesitate to say this, but what does this what would this even imply for us philosophically if a question of a parameter value that appears fundamental in the standard model is actually a question about early universe dynamics? And last of all, why would nature do this to us? Nonetheless, if I got locked up somewhere like, I don't know how to pronounce it, Archetri, it wouldn't be the worst thing in the world to be punished for heresy, especially if you end up standing on the right side of history.
Questions? So there are also people online, but we start with I mean, just because it's closer to me.
All right, thanks, Matt. One comment, Galileo had very clear observational guidelines to what he did.
Yes.
It was the opposition that didn't have this guidelines, they had philosophy.
Yes.
That's one. Second, in your model, by the time you add TV stuff, why can't you just have the TV stuff reduce the scale of instability to start with? Maybe it doesn't need to be TV. Just some weakly coupled stuff to bring the what would have been the, you know, algae-induced standard model instability to happen at the TV.
Yeah, so that's what we do. So
Okay.
yeah, so we add it.
No,
exactly. So we add it. No, good point. So it has no influence below the scale of its mass, of course. And so to get it to force it to go negative at the TV scale, it has to be light. And so that's the reason. By the way, about the observational evidence, I'm totally agree with you. I think we have to, ideally, I would rather, as you know, I spend a lot of, not too much actually, you couldn't spend too much time on it, but I spend a lot of my time arguing for future collapse. I think ultimately we need, the only way we will answer these questions is to go to higher energies and really explore.
Many of the things that we discussed have pretty precise predictions, right?
Yes.
I don't know if this was Fear's question, but
That's it. End of story. You saw something going around the sun. But their stuff, their heretics, as far as I remember, there was clear evidence, you know, that the general tomorrow, the rock. I don't see that anything that.
Well, the standard model breaks down. So unless you can answer that first question, if you can, awesome. But if you can't, and I don't think you can, then we know the standard model breaks down. So there is, the standard model gives us the evidence that something has to exist at higher energies. Yeah. But yeah.
so I mean, if you want to dispose of all this stuff, you get into much crazier theoretical territory. So let's say that we imagine that okay, if you have the standard picture with SUSY at some scale below quantum gravity and the X mass is calculable, then the problem is very precise, right? I mean, you see it at 3 level. It's nothing murky. It's not deep.
There is no, as far as I know, tell me otherwise, but there is no, Galileo had a positive hint, he made the calculation, he got the result, compared it to data,
No, but
and then got
you're-
into trouble.
all these as in abandoning symmetry solutions or as in thinking about the problem at all?
Yeah.
Look, I don't have a better idea. I'm not too positive about it. Just pointing out that there is a fundamental difference between the Galileo observing.
By the way, Kafir, you may be
Well, so sorry, I don't want to hijack Matt's thought. I think we should, okay, sorry, I'll let you answer.
no, but
But-
let me my insinuation about the heretics in Galileo wasn't about so much about what you're saying about, you know, the program. It was more like that perhaps people working in this are the heretics, and the people holding on to the MSSM are on the wrong side. So that's wasn't intended to be a question about defending, you know, drawing clear analogies between tides and things, you know, the Galileo's arguments and this, where I agree that, you know, he was swamped in data and somehow still people didn't believe, whereas we're in a slightly different in a different paradigm.
So speaking of data, so let's just pretend that, I don't know, RK flavor anomaly or G-2 or something points towards TeV scale or above states that couple to the Higgs. That will make the hierarchy problem sort of beyond reproach, I would think, because then you have calculable Higgs mass contributions.
Well, no, because
No?
so say you just couple the Higgs to some other heavy states.
Yeah.
Then the Higgs mass is still not a calculable thing. It has to
No.
be really predicted by
No,
the theory.
no, sorry, that's right. But there's a contribution that's already by itself troublesome.
No, because in that, yeah, I mean, yes and no, in the sense that yes, if G evolved down above that scale, you have IR calculable pieces which are
Right.
big.
Right.
But on the other hand, still, unless you have a theory that's like pions to QCD, where everything is, or SUSY, where things are really truly calculable, it's a counter term. You measure the mass and you carry on. And so, but which is, you know, that would mean the end of 2 millennia of reductionist science. You know, that's the most extreme thing. But I think already one doesn't need to discover that the heavy states exist to defend the hierarchy problem.
Oh no, so I agree with that. But you know, if I wanted to sort of adopt a Minnesota-esque attitude, then the way to kill the Minnesota-esque attitude is for there to be a TeV or above stuff that couples to the Higgs, because that is something that I cannot wish away. You know, because within the standard model, there are no calculable contributions that are a priori a problem.
Yeah, I don't know. I mean, if you look at
That's not my question. My question is, let's just say that we do have these heavy electroweak states that we discover for some other reason. And then they do give us some contributions all by their own. Would this change any of this picture?
Yeah, I mean, it would change what I do with my time,
Well,
because I would be studying those states and
right,
trying to figure out what's going on in the structure. I wouldn't be spending my time on these bigger, I mean, we may end up asking these big questions again, but if we discover new states, we experiment the hell out of those states and figure out what's going on.
If I understand it, you seem to say that all these approaches, they imply existence of new physics at the TeV scale.
No,
No,
that's the question.
These are
Do they?
misunderstood. Okay.
Yes.
Because if it's true, this destroys a bit the whole motivation of these models, it seems to me.
The motivation of these models is not to hide. It's not to hide naturalness. It's to ask: does cosmology play a role in the question of naturalness? You know, nobody wants to make an undiscoverable theory here. But what we're trying to do is understand why the Higgs would be lighter than the UV cutoff. All of these models seem to require either states at the TeV scale or very light, weakly coupled or weakly-ish coupled scalars and things like this. So all of them appear to me, at least, to be discoverable in some way or another. But that's a good thing. But I don't think anyone's trying to.
But these new
The
states are
goal
not,
of these models is not to get away
electroweak.
with.
Do they have to be electroweak charged though, or?
Well, no. So not all of the models have electroweak charge states, but some of them do.
Okay.
the relaxion, the model, our model, sliding naturalness, right? You would, if you were to address the strong CP, you might have to go down the same road as the I see.
Well, also the relaxation, if you didn't have to solve the theta angle, would not need the new states at the TV scale.
It does, yes, yes. So I can't quite hear you.
Okay, anyway, so I'm just saying that also the relaxation, I think in the version we just where the potential is induced by the QCD,
Yes.
it doesn't need the new states.
But then
at
you
the TV
predict
scale.
a big strong CP angle,
Yeah.
so that's ruled out.
Okay, now it would be very interesting if it's a theorem that all these approaches they imply existence new physics at the TV scale.
It's not exactly a theorem, but you need an operator. Most of the ones that want to describe with a scalar, you need an operator sensitive to the X value. So if you do it with new physics has to be lighter than the X if you want to do it naturally. So there is no theorem, but in practice,
Yes.
almost.
So we take maybe a few questions from the people online. I saw that Michael raised the hand and also Xing Yang.
Yes. Is that my turn? Can you hear me?
Yes.
Yeah. So the old picture of electroweak symmetry breaking, for example, the potential receives some thermal corrections and then develop from a symmetry point to a Mexican head type of potential. Is this picture still valid? As far as I can see, it's similar to one of your scenarios, but I'm wondering whether is this still a viable approach? And the second question is, yeah, thanks for the very nice summary of all the different approaches. Are there any clear experimental prediction that can distinguish all this? Each of them has predictions that can be used to distinguish from other mechanisms.
So the first thing is that whether it's the Gibbons-Hawking temperature during inflation or finite temperature effects, they all need to be they all need to be during whatever this dynamics is. In these models they need to be smaller than the electroweak scale. Whichever those two is bigger, they're required to be smaller than the electroweak scale. Otherwise, those corrections would lead to corrections to the effective Higgs mass squared, and you'd end up solving the wrong hierarchy problem because then those would change after the evolution. So that picture sort of still holds in most cases, but during the evolution, those corrections have to be small. On the other hand, after, for instance, inflation, one can, in many of these models, reheat, not all of the models, but one can reheat the standard model sector to be above the electroweak scale, and all of that evolution for most of these models looks the same. So that doesn't impose a large post-inflationary constraint, although in some cases it does impose some. The second question about the experimental predictions. So I would say that there's no single one that's common to all of them, but there is there are two main things, which is that all of them, I think, sort of tend to leave imprints in cosmology. So there are some fingerprints left around in various aspects of cosmology, whether it's ineffective or requiring very long inflationary epochs and things like this. And so I think precision cosmology has a lot to say about a lot of these models. And the second thing is that intensity, a lot of them have, light, weakly coupled scalars in the game, which is, apart from one of the models, they were all of sort of that, the rest were all of sort of that class. And so the intensity frontier plays a big role. And I would say that the intensity frontier from the Higgs mass down, so there's a big gap in the intensity frontier at the moment, which is from about the bottom mass all the way up to the electroweak scale. I think coverage of that window at the intensity frontier level would be good, because and going to lighter masses and smaller couplings is always a good thing. So those are the two main places where new physics imprints of these models could raise themselves. And then the last place is that, as we discussed, in some of the models we get electroweak scale states.
Michael?
Yeah, maybe I can. Sorry. So Thanks, Matthew, for the very nice talk. But maybe I can ask my question after the discussion, since we're already running late. I think it's more a discussion type question than.
Well, that is not. I mean, in the previous days, the discussion, let's say, happened. Was diffused. So I think you can go if you want.
Yeah. Okay. So, so first of all, to answer Matthew's comment about our work, I agree that that in our work, I mean, about the inflating to the weak scale, there indeed it requires eternal inflation, and that seems to be a common theme among many of these papers. So so that's why I wanted to raise this question of whether we could say something despite this being eternal inflation, and B, whether it could be avoided. So at least I think the answer to question B is that maybe. And I think that it's worthwhile to discuss this maybe further.
Yeah, I agree. Can I change the slides here? I do. Here we go. Yeah, so this was this, is climbing calculable? Sorry, I didn't, yes. Okay, super. Yeah, this was this question, is climbing calculable? I think it's a really important one. What weight do we place on this? You know, do we want to, is it super important to have a non-eternally inflating model? Is that an existence proof where an effect is calculable? So at least you have confidence that there's something there, even though perhaps eternal inflation was eternal? Or are we happy with models that rest on the assumption of eternal inflation, given that inflation has been argued to be generically not guaranteed, but it's, you know, for the most part, if one were to somehow place some priors on model space, that lots of models want to eternally inflate. I really don't know how to interpret this yet. Which is why I put this question. I completely agree with you, but maybe little existence proofs of non-eternally inflating models are useful because they show that at least some aspect of the predictions can be decoupled from that assumption.
Right. I also think. Sorry?
No, go. I also have a question related to that, but you can go first.
Yeah, so I mean, I think the one problem about eternal inflation, which is not even related to the measure problem as you define it within your like low energy effective theory, it's that eternal inflation is actually sensitive to the full UV structure of the theory, right? So you even playing within an EFT in eternal inflation might be problematic, since you are already putting some constraint that, you know, most of the interesting dynamics happen within the subset of the theory which you see in the low energy, while there might be a much more complicated and interesting dynamics that completely destroys all the dynamics you're describing within the UV theory, within the heavy fields. So that's why I'm thinking that even answering that question, answering that question I think is very interesting, even in terms of you know, making progress within some mini EFT, but I think there will always be a question of what kind of UV theory what kind of stress on the UV theory is this putting? That's
yes. And there's a further aspect. Sorry, I'll just comment on the before Raman. Further aspect, which is that typically theories that eternally inflate are in the swampland. So even our stringy picture of what the landscape looks like in that context might be completely wrong. And so indeed UV effects might be important, but I don't even know how we start discussing them, on what footing.
So one question I had is like related to the cosmological constant. So usually, let's say in symmetry-based solution of the hierarchy problem, we always think the cosmological constant like something separate somehow that can be addressed by Weinberg argument or landscape. But here, let's say, it seems to me that, since you are already living in eternal inflation, you should basically address, the only real solution would be addressing both problems at the same time, right? You cannot somehow ignore the cosmological constant problem.
Yes.
Somehow you are reintroducing it and you cannot solve it with the usual, let's say, generic landscape. You need to, you know.
Yes, I agree. So it's I mean, so they're coupled and decoupled in various ways. So for instance, if we go back to the relaxion, I'm just picking this model because I know the answer, not because it doesn't apply to other models, but you can't predict precisely which minimum you live in here. And so, and the height difference between these minima is of order the QCD scale. And so there's a very odd thing that if there was some non-anthropic solution to the CC problem, it would have had to have known in advance which minimum you're going to land in, even though it can't have known that. And so it does raise, some of these models do raise the question of the CC problem to a different level than you would have if you weren't talking about electroweak naturalness. In different ways for all of the different models, actually. And so it does change how you frame that. Although in this case, at least, I think you could probably still just appeal to anthropics, but it depends if this is also, these models require large decay constants. So unless you appeal to something like clockworking or something like that, then naively you're in the swampland here as well. So there's some interesting dialogue to have there, but I don't really know what the answers are.
I think you can just unmute yourself.
Me? My next. Yeah. So I liked the last question you ended the talk on, which was why would nature do this to us? And it just seems like that criterion, that question, sort of distinguishes some of the different scenarios that you discussed. Of course, just to sort of calibrate, as you know, the pi plus pi zero mass difference is one of those beautiful examples of naturalness of a QED-like scalar, where naturalness actually works. Yep. Where the cutoff of the chiral Lagrangian basically is related to the mass naturally. And it turns out that nature did not require any relaxion mechanism, no strange mechanism was required. So if I just take, let's say the self-criticality localization mechanism of yours, there's always this alternative, right? That could be going on, but apparently to just get some sort of electroweak symmetry breaking, or in some technicolory way, through compositeness or standard SUSY, that would have been the alternative. And so in any of these setups, you sort of you not only want to say, here's the mechanism for what I want to propose, but here is somehow my worldview of why the dumb, simple thing couldn't happen. Like there's some other calculus going on where the dumb, simple model is sort of obstructed in some way. And I don't know whether that is somehow secretly got an anthropic side to it. But just as an example of one of the scenarios that you gave where, in a way, it answers this question is in the n-naturalness case. So if I just buy the mu-like problem for a second, then the question of why wasn't something simpler done is answered, because it just says, look, there's some n of these sectors, and we're just reheating into the, by chance reheating with some very moderate tuning, not fine tuning. We are reheating into the lightest sector, and that turns out to be 1/√n lighter than the cutoff, just by standard statistical thinking. So it kind of answers that question, whereas some of the other ones sort of require you to think that a standard mechanism is somehow off the table, and you have to go to these greater gymnastics to get there. So I'm wondering if, anyway, that's my comment, but I'm wondering if you have a view on that. That was a great question, that question F.
Yeah, so I have two views on that. So on one side, there's still the question in that case of why the N, why this big N, where did it come from? And
there we don't really know, do we? I mean, I asked I asked Shamat Katru, you know, prominent string theorists.
Yes.
What's wrong with having like a large rank gauge group, which ultimately fragments into many sectors? And what do we know? You know, even as a string, even if I just believe string theory dogma, what kind of bounds are there? And he pointed me to some papers and so on by Candelas where they tried to estimate the ranks of groups or product groups. And the answer is it could be enormous. It could be enormous.
Yes.
So I don't know whether that may just be that's the way it is. Why are there many galaxies? Why are there many gauge groups? I don't know. You know.
Yeah. No. So yeah. It is very different. I mean, in one sense, the other models that sort of scan each point on the potential is a sector, and those sectors are being realized not all at the same time, but sort of at different times. So by the way, you know, I should say I'm not given up on even more vanilla style thought ideas. You know, I'm still working. You know, my most recent paper was along those lines of something that's very much like a tweak of pions. On the other hand, you know, I am drawn purely on an emotional basis to the notion that actually what the LHC has told us is super revolutionary. And so these models that sort of depart radically from our normal effective field theory logic, and I do think naturalness is a very clever scenario which is still consistent with effective field theory logic in sort of the more basic sense. And so these other ones, I find them interesting because they are so radical, and so it would really mean that, you know, this point E, you know, what would this mean for us philosophically? It completely changes what we mean when we talk about the values of parameters. So I'm drawn just purely out of academic interest, but no, I think because these things are so radical. But I don't really have a strong viewpoint about aesthetics and priors on these. I'm nervous about theoretical priors in the first place. Not a very good answer, I'm afraid. But
well, actually, I don't even. I mean, I was curious to hear your answer, but I would say I applaud all the efforts that you just reviewed, because we are going into the unknown, and I think one of the questioners had sort of said, well, you know, Galileo had data, and apparently we are philosophizing in the absence of data. But I would say I agree with you that what we have not seen at the LHC, in my view, is data, right? And so we are confronting that absence of physics beyond the standard model and are grappling with it. And I applaud all the efforts because I think we're at the beginning of it. I only say, to me, your question F is a kind of razor that I ask myself in each case. Mm-hmm. Not only how did the authors get what they wanted to happen, but why couldn't nature have done something vastly simpler, like just give us boneheaded Technicolor or, you know, something like that? So it's really just a comment more than a question.
So yeah, I think that we might want to try to move on to the next speaker. Maybe I'll use my privilege as an organizer to make one last comment in response to the last thing that Raman said. So essentially, I agree with what Matthew said, but in the end, the question, the way Raman, you proposed it to us, implies that simpler is better, but to some extent, this is just us. I mean, it's a human construction, and we had all these priors about grand unification showing up in the 80s or whenever it was that they did the proton decay experiment, then SUSY at LEP, etc. I mean, I just want to say that all these priors that we had based on simplicity have failed before. So I don't know, in my personal view, all these attempts are just a way to be humble. I mean, they are an alternative possibility, which might look a bit baroque from our point of view, but maybe nature has decided to be a bit baroque. And well, I mean, yeah, as Matthew said, I mean, the LHC, I mean, this is one of the biggest lessons of the LHC, that maybe that nature wants to go.
yes, and also nature's already said it's not minimal.
Yeah,
The standard
I
models
mean,
are
already
nice.
the standard, exactly. The answer to your last question is nature has already done it to us. It's the standard model.
Yes.
Yeah. No, I guess I didn't mean minimality in counting particles, but
Yes.
that in any scenario, you get to decide in which way Occam's razor acts. That's all. I mean, you get.
I'm going to just comment if I mischaracterized anyone's work. By the way, I'm worried about Raffaele's answer to my question about strong CP. Then please let me know, and I will correct the slides.